So today we're going to be talking about light and quantized energy. So basically, light is a form of electromagnetic radiation that has characteristics of both a wave and a particle. So the wave nature of light is visible light is a type of electromagnetic radiation, a form of energy that exhibits wave-like behavior as it travels through space. Other examples of electromagnetic radiation include microwaves that cook your food, X-rays that doctors and dentists use to examine bones and teeth, and waves that carry radio and television programs into homes. There are different ways to characterize waves, and all waves can be described by several characteristics, a few of which might be familiar to you from everyday experience. You might have seen concentric waves when dropping an object into water, as shown in figure 5.2a, so a ripple. The wavelength, represented by A in the Greek lambda, is the shortest distance between equivalent points on a continuous wave. For example, the wavelength is measured from crest to crest, or from trough to trough, sorry. Wavelength is usually expressed in meters, centimeters, or nanometers. The frequency is the number of waves that pass a given point per second. 1 hertz, the SI unit of frequency, equals 1 wave per second. In calculations, frequency is expressed with units of waves per second. The term waves is understood. A particular frequency can be expressed in the following ways. 6.52 hertz equals 652 waves per second, or 652 per second. The amplitude of a wave is the wave's height from the origin to a crest, or from the origin to a trough, as illustrated in figure 5.2b. Wavelength and frequency do not affect the amplitude of the wave. All electromagnetic waves, including visible light, travel at a speed of 3.0 by 10 to the 8th millimeters per second in a vacuum. Because the speed of light is such an important and universal value, it is given its own symbol, c. The speed of light is the product of its wavelength and its frequency. And the electromagnetic wave relationship is expressed below in this graphic right here. So here is where you can learn about all of that in the relationship between electromagnetic waves. Let's just get rid of that. There we go. Okay. So now moving on down, you can see different examples of waves, and these illustrate the relationship between wavelength and frequency. And as wavelength increases, frequency decreases. So here we can see a lower frequency, which has a longer wavelength compared to the shorter wavelength that you see here. It's much longer up here at that lower frequency. As the frequency gets higher, the waves become more consistent. And although the speed of all electromagnetic waves in a vacuum are the same, waves can have different wavelengths and frequencies. As you could see from the equation on the previous page, wavelength and frequency are inversely related. In other words, as we explained, as one quantity increases, the other decreases. So here we're going to talk about the atomic emission spectra, and basically the atomic emission spectrum of an element is the set of frequencies of the electromagnetic waves emitted by atoms of the element. Neon's atomic emission spectrum consists of several individual lines of color corresponding to the frequencies of the radiation emitted by the atoms of neon. It is not a continuous range of colors as in the visible spectrum of white light. And that's all. Thank you.